All right. So the common ion effect. First slide. I'm just going to bring the whole thing up, and you can write this all in. All right. So this example here is a little different than what I just discussed on the board. Given the following equilibrium system, PbI2 solid dissolving into Pb2 plus and 2I, and then I've got 1 minus or minus 1, it doesn't matter, it could have just been minus. Now this particular slide describes the common ion effect again as a Le Chatelier situation, which is fine. So the question then is posed, suppose a solution of sodium iodide was added to the system. Sodium, being a spectator, we know does not participate in very many chemical reactions. With that blank space beside the arrow, I'm looking for what sodium iodide will become when it is aqueous and when it is dissolved. So I'm simply looking for an Na plus aqueous plus an I minus aqueous. And so by adding sodium iodide to a solution that already has lead 2 iodide dissolved in it, we have a scenario where we have a common ion. And this isn't really, earth-shattering. What's the common ion between lead 2 iodide and sodium iodide? Yeah, it's iodide. So this is not earth-shattering stuff. But we do really need to pay attention to that. The common ion is the iodide ion. So as I was stating earlier on, that's going to change the values that are in the KSP equation. It's going to change the equilibrium. It's like we're shifting the equilibrium, if we think of it in terms of Le Chatelier. By adding iodide, according to Le Chatelier, so if the concentration of the iodide increases, that means that our equilibrium should shift left. And if the equilibrium shifts left, then we're going to have some more of the solid that was dissolved in the solution come out of solution, and a precipitate forms. Even if there's solid lead iodide sitting on the bottom, a precipitate will form. And it'll settle out, and we'll have a new equilibrium. Another way of thinking of it is that last bullet, therefore the solubility of the PbI2 is reduced. Essentially, that's the common ion effect when it comes to solubility. The solubility of a substance that is not very soluble in water, well, for all substances, but we see it when we're talking about things with a small KSP, decreases when there's a common ion in the solution. So, just as a statement, the molar solubility of a salt is reduced due to the presence of another salt having a common ion. That's just the statement of the common ion effect. It's been stated multiple times already this morning. Now I'm quite sure that these example problems are on your sheet, so you can that's the sheet I gave you yesterday. You don't need to write them all out. And then the practice problems are on the bottom of that big sheet that I gave you way at the beginning of this discussion of solubility. All right, so let's proceed with some example problems. And as I stated with you already, I am going to ask a question, and this is the way it's going to look on the test. Determine the molar solubility of lead 2 chloride in pure water, which is your straightforward MX, M2X shortcut. Determine the solubility calculation. What is it in 0.2 molar lead 2 nitrate? So in this case, we've got a common ion of lead between the lead 2 nitrate and the lead chloride. I probably won't ask you 3 on the test. I really just want to know if you can do the shortcut and if you can do a common ion effect problem. Here I've added an extra one, calcium chloride, so that we can see the effect of the chloride common ion. All right? So let's go ahead and solve this problem. Lead 2 chloride, I don't have the KSP for lead 2 chloride right there. Could you check on your little KSP sheet if you have it nearby? What do we have here for the KSP for lead 2 chloride? I will give you all that information on the test. Yep. 1.2 times 10 to the negative 5. 1.2 times 10 to the negative 5. All right. So let's determine the molar solubility in pure water. This is PbCl2. For pure water, we do not need to write out the entire thing, but I'm going to write it out anyway, plus 2Cl minus. Because for pure water, it's the shortcut. That means we're going to have 0, 0, all right? And I'll write it out just to stress the difference between the pure water and the common ion effect. This is a review, essentially, of how we did the MX. 0, 0. That's what makes this pure water. In the common ion effect example I'm going to do in a moment, we're not going to have a 0 in the initial. And that's because of the common ion. And that's what makes the common ion different than a regular pure water shortcut. Determine the solubility. And then we have X and 2X and X and 2X. And then we do the derivation. KSP equals X times 2X squared. But if you know the shortcut, use it. Trust me, on the test, the pure water one is going to be out of 2. Give me the equation, put the numbers in, and get an X to get the solubility, right? But this is a review. So without me going along and trying to remember that this is an M2X, what is the X equal to? Remember, we had a way of doing that. 1 and 2 determines the type of root we need. Yep, cubed root. The 1 plus 2 is a cubed root. Cubed root. Then it was KSP on top, and then what was on the bottom? 4, because it's 1 to the exponent 1 and 2 to the exponent 2, right? Because the exponents come from here. There's my 1 to the exponent 1. That's where the 1 to the exponent 1 comes from, because there's a number 1 in there that we don't write down. And there's the 2 to the exponent 2, which means we end up with a 4 on the bottom. And let's just put that in and do that. Cubed root of 1.2 times 10 to the negative 5 over 4. That was review of how we deal with solubility in a pure water scenario. Like I said, that's going to be worth 2. You don't need to write all that stuff down. But don't screw up the shortcut. That's your, you know, if you need to write it down because you can't remember the shortcut, that's fine. I'll take a number when you get it. What we got? 1.44 times 10 to the negative 2, and that's moles per liter. Make sure you put your units, and I apologize for writing it up the side there. All right, thumbs up on that. Did we like that one? Okay. So now let's continue on and talk about how this value of X, how this solubility is going to be affected now by the presence of some lead 2 nitrate. Okay? So I'm going to have to advance the slide in order to see that guy. So again, even though it says it's in some it's in some lead-2 nitrate, I'm still worried about the lead iodide, PB, what am I doing? Are we doing lead iodide, lead chloride? We're doing lead chloride. The lead iodide was my first example. We're doing lead chloride. Lead chloride. PbCl2, solid, Pb plus 2. I know it's lead nitrate, but that's my whole point. That's very important to know. Lead nitrate is soluble. All nitrates are soluble. We're still worried about the solubility of the lead chloride in the presence of this lead nitrate. So I'm still looking at the solubility of the lead chloride. That's what the initial question asks. And this is where students drive right off the road on this stuff. It says, determine the solubility of lead-2 chloride in some lead nitrate. So I've got a solution that contains some lead nitrate, and I want to try to dissolve the lead-2 chloride. I want to figure out how much lead-2 chloride will dissolve in the lead nitrate. So my ice table is the same. I'm worried about lead chloride. The only difference is my initial concentration of lead. And that initial concentration of lead is going to come from the presence of the other stuff, the common ion. So even though it says we're dissolving it in lead nitrate, my question is still about lead chloride. And what I've got to do now with my ice table, I don't care about the solids, that's still 0. But in this, I got to figure out if I have, 0.2 moles? If I have 0.2 moles Pb plus 2 initial, 0.200 moles per liter of lead-2 nitrate, PbNO3, and that's a 2. How many leads are in each lead-2 nitrate? How many leads are in each lead-2 nitrate? Matt? 1. So how much lead is in that lead-2 nitrate? 0.2. It's the same. Moles per liter of Pb plus 2. Because it's a 1-to-1 ratio. That's that mole ratio we talked about yesterday. Which means this number is 0.200. That's the hardest part of a common ion effect problem. It's crazy, but it is. We need to keep in mind we're still talking about the solubility of lead chloride. We now have some lead in the water because of the lead-2 nitrate, and that number needs to go into the initial. And now we analyze it exactly the same way. We're still looking for x. This is going to be x. This is going to be 2x. This is going to be 0.200 plus x, and this is going to be 2x. I'm just going to isolate this little calculation here from the others so that we can now continue with the solving. We're going to now solve it the same way. The k, which was 1.2 times 10 to the negative 5. 1.2 times 10 to the negative 5 is equal to, now I'm going to have 0.200 plus x times 2x squared. This is a little scary because I can't take any square roots on this one or even cubed roots. And if I expand this through, I'm going to have an x squared times an x. I'm going to have an x cubed. And I can't solve for x cubed. So I need some way to simplify this. What do I use? If I can't take a square root or a cubed root, and I can't solve for x cubed, what do I have to do? Yep, Matt? I have to check for the approximation. So let's check for the approximation. How do I check for the approximation again? How do I check for the approximation? Matt? Yeah, very good. 0.200 divided by 1.2 times 10 to the negative 5. And what do I get there? Something bigger than 100? Just round it to the nearest 1,000 or something like that.
1.6.
So that's about 10,000. Well, I'll write it down. Equals 1.6 times 10 to the 4. To the 4, which is greater than 100, which means the approximation is good. So when we have a common ion effect problem, we've got a number in here for the initial, comes from the solution it's dissolved in. We will end up needing the approximation every time. All right? So you got to check it. Which x can I get rid of? Looking like Matt's ready for the test. What do we got, Matt? The x that's added to the 0.2, because it's going to be such a tiny little number, it's not going to affect that 0.2. Now we can solve. 1.2 times 10 to the minus 5, 0.200, and I'm going to bring this through the squared, 4x squared. I can now bring these two multipliers down to the bottom, 1.2 times 10 to the negative 5 divided by 0.200 divided by 4. That's equal to x squared. So I'm going to take the square root of both sides. That drops my square away, leaves me with an x. .2 times 10 to the negative 5 divided by 0.2 divided by 4, then square root the entire thing. And whether you do that in one shot is whether, you have awesome calculator manipulation skills. Amelia, you're willing to give up your number? No, you're not willing to give it up? Caitlin, what do you got? 3.87 times 10 to the negative 3. 3.87, we'll go to two significant digits, so 3.9 times 10 to the negative 3. And that makes good sense. We've got negative 5. That might get us down to negative 6 by dividing those off. And then we take the square root. Do we like that one? And again, that's in moles per liter. All right? Now, just for comparison purposes, I'm going to go back to the last slide here. Take a look at what the solubility was in pure water. In pure water, it was 1.44 times 10 to the minus 2. All right? That's how much dissolved in pure water. And once we added the common ion, it's 3.9 times 10 to the minus 3. We've decreased the solubility. Less can dissolve. That's the common ion effect right there, the fact that there's a minus 3 in that position. Moving on to C, it's exactly the same. Again, we want to test out the solubility of the PbCl2. Pb plus 2 plus 2Cl minus. I'm trying to squeeze it in a little more this time because I almost ran out of room. Again, we need an ice table. Another common error on the test, folks, is when you get to a solubility problem, you forget to not include the solid. Keep that in mind. Because on the test, there'll be regular equilibrium problems with all gases and all aqueous. So you'll need some on the top and the bottom, but then there'll also be some solubility ones. And what are we dissolving it in this time? We're dissolving it in, could somebody tell me the question? Amelia, what does it say? 0.05 moles per liter of calcium chloride. All right. So if we're dissolving it in that, what's the common ion in the calcium chloride that we're worried about? Yep, the chloride. So I need to figure out how much chloride to put in there in the first one. Cl minus. Well, what do I need to do with that number for the calcium chloride to get me the chloride? This isn't earth-shattering in any way, yeah? And what is it? How many chlorides are in each calcium chloride? So I need to double that number. When the chlorides fall off, I'm going to end up with twice as much chloride. 0.05 times 2. 0.10 moles per liter of chloride minus. That 2 comes from there, and that leaves me how many chlorides there are. So that simply means I have a 0.10 in that position and a 0 for the lead. And now I'm going to try to dissolve it. I'm going to go through this exact same procedure as I did in the past. You guys could probably go ahead. You will need an approximation check. There's one little pitfall that you got to watch for, and I'll tell it to you when I catch up to you guys. So, x, 2x, x, 0.10 plus 2x. 1 point, you'd think I'd know this k already. 1.2 times 10 to the minus 5. 1.2 times 10 to the minus 5. That's going to get me x times 0.10 plus 2x, and that's all squared. Now I'm going to check for the approximation. What number am I putting on top to check for the approximation? What do I divide to check for the approximation? (0.1), the number that's being multiplied. 0.10 divided by 1.2 times 10 to the minus 5. Yeah, that's going to be greater than 100. You're going to do a little check on that. The approximation is good. What am I getting rid of? What can I say is essentially 0? Which value of x? Yeah. It's the 2x. It's the plus 2x. This thing is tiny. Can't make the other one 0. The whole thing becomes 0 if that happens. Now here's the little pitfall that many people fall into. Now you're ready to go. 1.2 times 10 to the minus 5 equals, excellent, you got an x in there, but we often forget that there's a square out here. We need 0.10 and it is squared. Don't forget that that square goes along with it as well. So I'm going to have 1.2 times 10 to the minus 5, and that's going to be over 0.10, and that's squared, and that is x. No need for a square root on that one. And I'll take the solubility of that when you get finished calculating. What do you got there, Matt? Times 10 to the negative 3. Again, moles per liter. And I'm not going to go 2 slides back, but recall it was in the negative 2, right? Again, we have a decrease in the solubility due to the presence of the common ion. Okay? So just to kind of review this particular type of question, right? Determine the molar solubility of lead chloride. I will give you the KSP right in the question. And then I'll say in pure water, shortcut. If you remember the shortcut, away you go. Get the solubility. And then I'll say, what if it's in a solution of something that contains the common ion? The common mistake is to write down, an equation for lead nitrate. But lead nitrate is soluble. We're not concerned about that. We're still looking for the solubility of the lead chloride. Write that down, figure out how much of the common ion is in there. There it is. Put it in your initial conditions. Solve like normal. No shortcut because we've got to treat each one individually, and it's because we can have any number in there for that particular value. And then you got to use the shortcut, or sorry, the approximation, and then away you go. Now, on your sheet, how many other examples have I got there? I do have 2 more examples. I've got all the examples. All right, let's take a look at this one. Determine the maximum concentration of fluoride ions that could be dissolved in a solution of 0.2 molar magnesium chloride before a precipitate of magnesium fluoride forms. Interesting question here. Interesting question here. I'm not even thinking I need the common ion effect to solve this. I think we could probably, at maximum concentration of fluoride ions that could be dissolved in magnesium chloride before a precipitate of magnesium fluoride forms. I think we can solve this with what we learned yesterday. I don't think we need to be as complex as having an entire ice table for that. If I were presented with a question like this, which obviously I am, start by drawing a little picture to think things through. What we have here is a solution that contains magnesium and chloride, all right? And we're asking the maximum concentration of fluoride ions that could be dissolved. In other words, I'm going to add something in here that contains F minus a certain concentration. And at some point in time, a precipitate of magnesium fluoride is going to form. Determine the maximum concentration of fluoride ions that could be dissolved in a solution of magnesium chloride before a precipitate begins. Mg plus 2. Oops, I needed 2 there. 2F minus. I know a number for the magnesium concentration. KSP is going to be equal to the concentration of Mg plus 2 and the concentration of F minus, sorry, it's squared. And without doing any fancy common ion calculation, but the reason this is a common ion problem is that I'm dealing with magnesium chloride and I'm dealing with fluoride, and that there's the common ion of, I guess, the magnesium, how much magnesium fluoride will be formed. So I guess it has a little bit to do with common ion, but not really. The only thing I'm missing here is this, is that fluoride ion concentration. It's the only thing that's missing. I can get a KSP from the table. I know the magnesium ions from the question. So why don't I just solve for fluoride? That's what we did yesterday. So why it falls under common ion, I'm not sure. Some textbooks put it there. So let's just go ahead and solve it. How much magnesium do I have here? Magnesium plus 2. I have 0.020 moles per liter of magnesium chloride, MgCl2. Therefore, how much magnesium is in there? Because you need the formula for all these things, so you can see how many magnesiums are in it. Yep. Because there's only one magnesium in it, right? So this essentially is times 1. 0.020 moles per liter. Well, why don't I just rearrange and solve and get my stuff? I'll rearrange first on this one. KSP over the Mg plus 2 concentration, and that's going to be equal to the square of the fluoride, so I'm going to take the square root of it. That's just a straightforward how much you can dissolve in it. There doesn't seem to be anything special in that question to me. Does somebody have a KSP for that? Yep.
6.4
Times 10 to the negative 9 over 0.020 square root, and I'm going to have F minus. I wouldn't even consider this a common ion problem. I will frame your common ion effect problem exactly like that first example we did, so you'll know when you get to it. Then I'll take a number for this. Looks like we've got like a -7 root, so it's like a -3 or -4. Yep. 5.6 times 10 to the negative 4, and that's again a moles per liter. Please include your units, folks. All right? So this one seems pretty straightforward. What's the matter? We're good? I wouldn't even consider this common ion. Some textbooks do, but nothing to be excited about. That's more of a yesterday's problem. 5.6 times 10 to the minus 4. Let's do our last one, and then we will be done for this. Okay. It was found that the molar solubility of strontium fluoride was 4.3 times 10 to the minus 7. And this is in a solution of 0.05 moles per liter of calcium fluoride. Determine the KSP for strontium fluoride. All right. Let's say you're throwing this question and you have no idea where to begin. If I encounter a problem that I have no idea where to begin, especially on a solubility problem, I look for the fact that I'm looking for the KSP for strontium fluoride. I'm always either going to be given the KSP or I'm going to be looking for it. And if I'm looking for it for strontium chloride, then that has to be the equilibrium I'm dealing with. So I write it down. Strontium fluoride, what is strontium? SR? SRF2. All right, it's in group 2. It's a solid. SR plus 2, F2F minus. So I start right away with that. If I'm going to need an ice table, it's that I'm going to need the ice table for. It was found that the molar solubility of strontium fluoride was 4.3 times 10 to the minus 7. What variable has molar solubility always been, right from the beginning of our discussion of solubility? What variable is molar solubility? Yep, X. Down here, I'm going to put X is equal to 4.3 times 10 to the minus 7. Molar solubility is X. In this case, they've given us the X. It's kind of neat. Let's look at the last bit of information. 0.05 moles per liter of calcium fluoride. I'm going to put this off to the side. 0.05 moles per liter of calcium fluoride, CaF2. What information am I going to get from that data? Yep.
0.1 fluoride.
Very good. The common ion is fluoride, and it's going to be 0.1 fluoride. That's excellent. Concentration of F minus is going to be 0.50 times 2, 0.10 moles per liter. Where's it going to go? Where am I going to put that number? Nothing earth-shattering here as well. Where am I going to put that number? Yep. Initial concentration for F. 0.10. Now I'm going to just proceed. I'm hoping that when we get our initial, we can proceed from there. X 2x, x, 0.10 plus 2x, KSP equals x, 0.10 plus 2x. Game plan at this point. What do you think, Todd? Sub in x and get your KSP. 4.3 times 10 to the minus 7, 0.10 plus 2 times 4.3 times 10 to the minus 7. Now you might notice here why we use the shortcut. Look at 0.1 plus 2 times 4.3 times 10 to the minus 7. I think that's going to be approximately equal to 0.1, right? Because of that tiny little x. You can run it through your calculator. Go for it. Run it right through your calculator. Do exactly what it says. But in that right bracket is going to end up being 0.1. You have an answer?
Isn't the second bracket?
Ah, yeah, we got to square it. Thank you. Squared, squared. Yep, very good. Very good. So that right side becomes 0.1 squared, but go ahead and run it through. And if you're doing it all in one shot, I really don't care. It's just you'll find that that's why the approximation does function the way it does. Yeah, what you got? 4.3 times 10 to the negative 5. Negative 9. And we know what happened. When I got the eraser out last time. We don't like negative 9. Did you square the 0.1, or did you? Well, actually, did you square the 0.1? Did you? What do we got? What do we want? Negative 9 or negative 8? We want negative 9. We got thumbs up on the negative 9. All right. Don't be afraid of the questions. The equations that you start with will be given by the question, what is the KSP of whatever the substance is? Or the KSP of the substance is this substance, that's what you're going to use. It'll often say, is dissolved in pure water. Please do not write an equation that has water in it. Many people will take this and in the pure water will say, oh, that's strontium fluoride plus water, and then somehow get who knows what they get. And that's because they haven't prepared. Not at any point in time during our solubility discussion have we ever actually put water in the equation. It's just doing the dissolving. So if it says it's in water, don't react it with water. Just have it dissolve, please. There's my rant on the end of the video. I really didn't need that, but it's there anyway. All right, so please, if it says is dissolved in water, do not actually have it reacting with water.